Okay, YouTube, this is my last video on my module on graphing linear and nonlinear inequalities in two variables, in which what we're going to do is really look at graphing a system of three or more, in this case linear inequalities, just to kind of see what kind of a region we would get for a solution region, and also talk about how these kind of look in terms of their equation or inequality format. So the very first thing we want to do to graph the solution region to find which points all three of these have in common is to rewrite these and graph them as if they are equations. So we say x minus y equals 2. Okay. In this case here, now this is interesting. We actually get two separate equations that come out of this. The first one is negative 2 equals x, and we say that x equals 4. So this is what we call a compound inequality. Okay, inequality, ineq. And then our last one here we would just say is y equals 3. So it looks like we have two vertical lines here and here, a horizontal line here, and then we have an oblique line here. So what we're going to do is just, I guess, graph these individually, being mindful of whether we need to make solid or dotted lines. So with our first graph here, x minus y is 2. Because this is in standard form, the best way to go about graphing this, of course, is just to find the two intercepts of this linear equation. So when we plug in 0, say for x, we get negative y equals 2, which means y is negative 2. And when we plug in 0 for y, we get x equals 2. So going ahead and graphing this first inequalities equation here, we would say that it hits at 0, negative 2, okay, here, and then we would say 2, 0. Now, because I'm supposed to use a dotted line here, or a dashed line, I'm actually going to go back and put open dots on these just because I caught it. If you put solid, oh well, as long as you put a dashed line through these 2 points. And so we're going to say this dashed line, when we label it, we're going to label it x minus y equals 2. And so we're going to come back and I would say that we'll shade this later. Okay, save the shading for last. Now with respect to our compound inequality, the interesting thing was we have x equals negative 2 and x equals 4. Well, these are both vertical lines. Vertical lines. If you know that x equals the numbers of vertical line, let's go ahead and graph these. But you'll notice that at x equals negative 2, this first one, we would use a solid line, where at x equals 4, we would use a dashed line. So at x equals negative 2, let's go ahead and pass our solid line through here. We're going to go ahead and label this with what its equation would be, which is x equals negative 2. Now, for x equals 4, we would say it would be the vertical line here, but remember that because in our inequality, our original inequality, it wasn't or equal to here, it was just less than 4, we're going to draw this dashed, so we say 4. So now last but not least, we say y equals 3. This would be a horizontal line at a height of 3, and because this is just less than, we're going to draw a dashed line that is horizontal at a height of 3. And so we get this right here, and all of these, the reason why we had been labeling them is because now what we're going to do is go back and test points on all of them to see which way we should shade. So in terms of a test point, the interesting thing here is this. If you notice, 0, 0 is on none of these graphs. And so since 0, 0 isn't on any of these graphs, what we're going to do is we're going to test 0, 0 in all of them to see if they work. So with respect to our first inequality, we had x minus y is less than 2. When you plug in 0 and 0, we would get 0 minus 0 is less than 2. In other words, 0 is less than 2, which is true. And so with respect to our oblique constraint, we're going to shade towards this side containing 0, 0. So up and inward here above it, we would say all of these points on that side would be solution pairs. Now with respect to these last three constraints, these are going to be a lot easier to check on because we can test the point. But to say also y is less than 3, we would say really with respect to that y equals 3 equation, we'd say that this is all y values underneath this. And you could see pretty clearly then also from our middle compound inequality, we say that we will shade all the x values between negative 2 and positive 4. So for x to be greater than or equal to negative 2, we would shade to the right of that constraint of the equation x equals negative 2, but we would shade to the left of x equals 4. And so what we're looking for is the solution to our system here. And so that is going to occur where all the shading happens together. So in terms of solution region, we want to be really critical in how we shade this in here. So I'm going to be really detail oriented, but we would see that we get this region right in here, and this is our solution region. So to point a few things out here, in terms of vertices, we would see that the vertices of our feasible region are these corner points. We could see that we get this bounded feasible region here that would have open dots on all of these points right here, because the only solid constraint or inequality we had was this vertical one in x equals negative 2, and it doesn't also run into any other solid constraints. So we have 4 corner points around this, what we would call bounded feasible region. So what I want for you to try then is with these three inequalities over here, we'll start calling them constraints, okay? I want you to graph them first and then go back and test a point to see which way you would shade on them if you need to test a point. If you don't need to test a point, go ahead and shade. But find this feasible region or solution region that contains all of the points that are solutions to all of the inequalities. Cheers.